Like they can accept compensation up to 200 pesos. Like that's a lot of money. Check it's like $3 in American. Like oh my god.
All right, we did this last class. Here's that truck. I'm going to review and then get to where we were, okay? It's an awesome truck, right?
That's a Suburban.
Yeah.
Oh, no, that's the other one.
It's a nice Ford.
I don't know what kind it is. It's homemade.
I don't know what these guys want.
It's a really big bumper. It's not shot.
Okay. Morning. So just a reminder, I'm teaching FEM next semester, vibrations, engineering economics at Capstone. Okay, so I did. I was going to teach 370, but that got switched. Yes. That I emailed yesterday. That should have been fixed. I'll have to check after class. Hopefully it was fixed yesterday before I left. So that it should move up to 35 students and do the online for that. Okay. So if you are, there's a few people that have class during that time. They're just going to do the online and then do everything offline kind of thing. Okay. So last class, a week and a half ago, we started looking at compressible flow. Okay. Really, you can spend a whole semester on this stuff, but really what we talked about, and we can label it over here, was isentropic flow. We talked about converging nozzles. And then converging, diverging. And we'll quickly review all these. And then we started looking at the shock waves, right? And we got the momentum down, but we'll kind of look at those, all right? So these are the basic ideas of compressible flow. And if you kind of understand these, you can further, if you ever get more into this field, this is the basics, okay? You can definitely understand everything else. So we also talked, if we have any type of flow, all right, and so here's the flow going over a truck. From 1 to 2, the actual flow will actually slow down, okay? And it will eventually approach 0, which is, what are those properties called when they bring a fluid to rest? Do you remember? Yeah. No. Stagnation. Stagnation. Okay. So you can have stagnation temperatures, you can have stagnation pressures, densities. Okay. The first homework problem on your homework is to plot that ratio between the stagnation temperature, T naught, to the upstream temperature. Okay. And I'll just give you the temperature one. What do we have right here? So the stagnation temperature was T plus V squared over 2CP. Okay. So this is just basic, actually using enthalpy. Remember what enthalpy was? What variable is that? No? H. Yep. H. So if you remember from thermo, H, or delta H, is Cp delta T. Okay? So we're using we're using a lot of thermodynamics in this for intermediate. They all kind of mesh together now. Okay? So we use this concept here, kind of in here. So if you ever want to know what the temperature rise would be in front of your car, if you put a temperature sensor there and you had a temperature sensor out in the world and you're not moving with it, you would see that the temperature sensor at this point too would be slightly higher, okay? Because you're bringing that fluid to rest. It's got to do something, okay? So when an airplane is flying really fast, okay, the front part is going to get really hot. Okay, that's a main reason why they have to design these, because you're bringing that fluid to rest, and it's going to increase your temperature, especially if you start going almost Mach, right? Because this number gets really big now, and this temperature difference is going to go up. Okay. What's that?
Just a little pay attention. You know, you're supposed to be.
Oh, yeah. When you look down, you can see.
Well, you already have, you
Yeah.
have probably cool at.
What?
You probably cool at.
Yeah. Really bad.
Makes sense.
Oh man, you guys are alive this morning. That's good. It must be.
Big day.
Okay, so this is problem 1 on your homework is to plot. There's I think 3 or 4 lines I want you to plot. So really, you're plotting the ratios between these stagnation temperatures. I think I gave you the sheets, right? Would you whip those
yeah.
sheets out? Did anybody not get those?
Sure.
I think I got extra copies.
Yeah.
Yes. No. Let's see here. Where is it here? Did I not give you those?
It's on the second page, right? Is that what you want? You might have a shock.
These are. I don't think I did. Let me give you those equations that I want you to use.
I don't have that.
You don't have that sheet?
Okay.
Let me see here. Where did I end up getting those equations?
These pages right here?
Yeah, that's for shocks, though. I didn't give you the other equations here. Where? Oh, right here. Okay, let me write those down.
Thursdays. I don't know what
Oh, it's Thursday.
Peanut. Oh, let's see. Let's do it this way. Let me give you these equations. So, it's weird. Well, let me look at something real quick. I thought I had my notes. Maybe I'm missing that page. Let's get right to the homework to help. Mm-mm-mm. Oh, no, yeah. There we go. One-dimensional isentropic stagnations. Yep. Okay. So these is basically, this is what I want you to plot. So P over P naught 1 plus k to the minus 1 over 2 m squared minus k divided by k minus 1. Density ratio 1 plus k minus 1 over 2 m squared minus 1 over k minus 1. Oh, am I recording? Yeah, good. And the temperature one is this one. And are we using air? Yep. So do you remember what K value was for air? Do you remember what the equation for K was?
You didn't give us these.
Did I give you those?
Yeah, I don't know.
Oh, okay. Okay, that's all right. Good review. Yeah, okay, so go back to K. Remember the number for K or the equation? Did I give you the number in there? Okay?
For K?
Yeah.
1.4?
Yeah, 1.4. That number is found in the back of the book. This is for air. And I believe it's CP over CV, if you ever want to know that. I think we did that in thermo. You should have that in your thermo. I think Alyssa has it in that over-exaggerated binder that you probably should duct tape.
Yeah, probably.
And you can plot these three right on the same graph, okay? And try using, so I think you'll get, I don't know, let's say you have 3 lines. They might do this or something. I don't know what they exactly do. And you could just call this ratio, and this would be Mach number. And use the text command and like put like P over P naught, T over T naught. Have you ever used that before? Text command in MATLAB? So you write text, parenthesis, then the X position, so say 0.5, and then the Y position would be 2, and then single quote, and then you can put P divided by P naught. That will put that at those coordinates, okay? Oh, there they are, right in front of me, those equations. Huh? Sorry.
I think you've checked out, Doc.
Must be. I had a week. Plus that Friday I didn't come in because of the weather. All right, so these talk about basically what the density does, what the pressure does, and the temperature. Okay, and you can see relationships between that. Now, that was looking at stagnation properties. Isentropic. So we talked, actually the students in thermo yesterday, see if they remember this. What did we talk about yesterday in thermo? Yes, we did that. After that, we talked about the Carnot cycle. Entropy. Good job, Will. You weren't there yesterday, but you remember from a year ago. That's good. So entropy. So we looked at Q over T plus so S gen. Yes, that's right. Good. Okay. So this is actually the second law of thermo. Okay, an actual equation that states that entropy will always increase. Okay, why? Because everything in the world has like some sort of friction or irreversibility that we can't get back. Okay, take a soda can that's hot, I don't know, put it in a cold room, okay, it's going to leave, right, that heat. It's going to go out. Okay, we cannot get that heat physically back unless we put it in a mechanical object to cool it. Okay, so that's what that means. But when we deal with isentropic flow, what does delta S equal? Do you remember? Yes. So delta S for isentropic flow is 0. Okay? Meaning that this type of flow is an ideal case. Okay? We're assuming that we can get that energy back somehow, but we know we can't. But it's just an ideal case. Okay? So that means this is isentropic flow. It's adiabatic, which means it's kind of insulated the system, and reversible. Now, what does adiabatic mean? It's insulated, meaning no heat transfer through the boundary. But what about the internal energy? Delta U. It could do whatever, right? Because think about it. Temperature changes inside a fluid duct if we take that as isotropic flow, is because the internal energy changes, okay, not Q. Remember, Q is heat through the boundary, okay? So we use this isentropic flow, meaning delta S is 0, assuming it's adiabatic, and reversible, meaning there's no friction losses, whatever. It's an ideal case, okay? We can do that, and we can actually figure out, I'm just going to give you one equation, and we do this in thermo. Students have taken thermo, you've done this. There's a whole bunch of more algebra that I don't want to show you, but I'm going to give you this. You can use this idea to get relationships between temperatures, pressures, densities, you name it, okay? So if we have flow in a pipe, and the flow's going that way, it's air, we can figure out what the temperatures and the pressures are at any point, okay? If we use isentropic flow. So this is a good transition. Now, if we have a pipe and we have somehow magically got a shock wave in here, right here. What is a shock wave to begin with first? It's some abrupt change in density, pressure, temperature that occurs, okay? If you somehow get that. Actually, the easiest way to think about it, if an airplane's flying faster than the speed of sound, okay, you're going to get a shock wave, all right? And that shock wave is basically due to, if you think about it, when you have signals being sent out at the speed of sound to let them know the flow ahead to say, okay, move for me. And it's receiving that back at the speed of sound, but if you're going faster than that, it doesn't know what to do. Boom, you get the shock wave, okay? So, and it's weird inside flow because they can occur, and it's all based on the back pressure back here. So the flow is actually going left to right here, okay? So depending on this pressure way back here, you can move this shock in this tube wherever you want. It's pretty crazy, okay? So basically you have Mach greater than 1 here, and then it becomes subsonic on the right side. Okay? So that's how shocks work. What kind of shock wave is that? Do you remember? Normal, yep, because it's perpendicular, yep. What can we assume the flow is in this black region to the left of the shock? And? Yeah. So, yep. We can assume that the flow over here is isentropic. And what about the flow on the right side? You can, still. Okay? But you can't do it over the shock because there's an abrupt change. Okay? So that's why we use isentropic flow to make our life easier to figure out what's happening up here and what's happening back here. Okay? So really, anytime you hear flow in air, we usually use isentropic flow. Okay? Same thing with gases. We use the ideal gas equation, right? Well, now you're dealing with fluid mechanics. Air is moving or a gas is moving. Typically, a lot of the times, we can assume it's isentropic flow. Make our lives easier, okay? Okay, so before I get to the full shocks, we looked at the converging nozzle. So say we have a pressure back here. We'll call it PB. What's going to happen to this if we keep dropping this pressure? What's going to happen to the flow inside that nozzle? It's going to start increasing, right? It's going to start increasing, and then the max is always going to be right here at the throat, right? what's the maximum velocity you can get right here at the throat? Mach 1, okay, which is the speed of sound, right? Okay. So you can drop this pressure to 0, and you're only going to get Mach 1, okay? Because it goes back to the speed of sound sending out signals, and it can't receive it back fast enough, okay? So, do you ever see rockets designed like this? Not ones that really want to go fast, right? So what they do is they do a converging, diverging section. Whoops, that's a weird looking one. Did we draw it? I don't remember. Okay. So you get Mach here at 1 when the pressure over here is low enough. Okay. Then if you keep dropping it more, what happens is now you could increase this speed to supersonic speeds. Okay. All right. And so again, let's recap. The only way to get supersonic speeds out of a nozzle, or this is a converging, diverging nozzle, is you have to have a converging section and a diverging section. So the pressure out here starts dropping, starts increasing the speed in this section, gets to a certain point when finally the Mach number is 1. And if you keep going down a little bit more, actually what happens first is you get a shock wave at really close to the throat. Keep dropping the pressure more, the shock wave moves to the right. Keep dropping the pressure even more, the shock wave then disappears, and now you have supersonic flow shooting out of there that you can reach a lot of speeds with, okay? So the big question for me, and I'm still trying to figure it out, is you know how right here the throat is only equal to Mach 1? Well, and I'm still trying to find it, and I can't figure out the reason, and I'm still doing it. I want to let you guys know before the end of the semester. If this signal is being sent out at the speed of sound, and it's trying to send back at the speed of sound, how can it get to supersonic speed? Right? That's my question that I can't figure out the answer with. And I never thought about it until you really, like, for you guys, you probably wouldn't ever think of that. But for me, to help explain it more, I need to know that. And so,
Because you're creating a vacuum.
you're creating a vacuum, but how, if the signal is being sent back at the speed of sound?
Because the signal is being sent out at the speed of sound, it's leaving a void here that the signal's not coming back. So with this new signal that's being sent out behind the signal is allowed to go faster.
But if we think about, let's go back to this one here, okay? In order, when this pressure is low enough, there is a signal that gets sent back this way at the speed of sound saying, okay, I can speed up, okay? But if this signal, if you're going at the speed of sound here, and the signal is being set at the speed of sound, they cancel. That's why you get Mach 1 here at the throat. But if you're going faster than the speed of sound, and this is going that way, it's always going faster than the speed of sound. The signal
So the
sends
speed
back.
of sound signal is never getting back to it. It's always
Yeah.
getting pushed forward by the faster signal, so it just keeps getting faster and faster. That's why it moves forward.
Maybe that's true. Maybe. Oh, I don't know. I'll think about it some more, but that could be it. Yep. But for you guys, as long as you understand this, and this is the stuff that when you start dealing with things and like really dive deep and say, okay, do I really understand this? Okay. But for you, as long as you understand, if you drop this pressure, okay, you get Mach 1 here at the throat. If you keep dropping a little bit more, a shock wave will start really close to the throat, okay? And then as you keep dropping this, the shock wave moves out, and then you have full supersonic speed shooting out, okay? Because if there is a shock inside here, right here, what's this going to be on the right side? It's not going to be supersonic, right? It's going to be subsonic, okay? So as long as you understand that, that will get you anywhere you need to go if you ever get more into this field. Okay. So. Okay. Yeah, I like that. It might be. I'll think about that some more. Thank you, Dan. Okay, so let's go back to shocks. So what we did is we took a control volume approach, right? I think we got. So in order to analyze what happens between upstream and downstream of this, we take a control volume of the shock, and what did we apply? What equations? Do you remember? What did we do in our paper?
Continuity,
Yep, and
momentum.
one more that we didn't finish, but we started, maybe.
Force.
So we did conservation of mass. We did momentum. So what does conservation of mass tell us?
M dot N equals M dot N.
Yep. And that's in this control volume, right? So if I have, let's make it brown here. So that's coming in, and that goes out. Always, mass is always conserved no matter what, okay? What does momentum tell us? What's MV1? Yes, no, yes, yeah. But what is m times velocity, or m dot times v? What is that? Like unit wise? Which is? Nope. If you have m dot times v, what's that? Force. It's a Newton. Newton. So what does momentum tell us? Forces. Okay? So what are the forces acting on this that you had written down? Remember?
MA plus the sum MD out minus MD.
Yes. Yep. So you have the force of the fluid pushing in, you have pressure on this side, and then you have m dot times v going out and pressure pushing that way. Yep. So the forces here are your m dot times your velocities and pressures. And we did those two. So with these two, you can find relationships between velocity and pressure. Okay? And what did we have for those equations? Let's write those down. So for the conservation of mass, we had rho 1 u1 equals rho 2 u2. I believe, right? Is that what we had in our notes? We actually call what we did it in continuity, right? So what is the continuity equation? What is that? What's the difference between that and when I say conservation of mass?
It has to deal with U's instead of A and B's.
They'll deal with the same thing. But what is the continuity equation that we wrote down?
Oh, it's equal to 0.
It's still conservation of mass, but in what form? Yes, it's differential form. And we wrote this down. So when someone says conservation of mass, you got to actually ask them back, what are you talking? Differential form? Or are you talking basic m dot algebraic form? Okay? You get the same, and we did both. You'll get the same answer. You'll get the same ratio when you do this. Okay? And then momentum. So when you have momentum now, let me write this down. We had what? P1 minus P2 equals rho 1 U1 U2 minus U1. So when we looked at conservation of mass, which is the Black-Stone equations, you can look at simple m dot 1 equals m dot 2. Okay. Or you can look at a differential form. Okay. Does that make sense, everybody? What about momentum? What are the two ways you can look at it that we've done in the past? Remember this? We did the, what was the problem? When we started looking at like the spigot and the water shooting out, what did we use to solve for the external forces on that? Not the continuity. Yes, they are called, Navier-Stokes. Yep, okay. So you could use the Navier-Stokes equations, which are in differential form, or you can use the famous law, second one? Newton's second law. Okay. So under momentum, it's Newton's second law, just like we did way back when we looked at the spigot, the water coming out, and we looked at the external bolts to hold it in. Or we can look at the Navier-Stokes equations, which are differential form of forces. Same thing. You'll get the same answer. We did both of those. Okay? And if you look, these two sets of equations are density, velocities, pressures. Okay? What is the other main thing that we're missing that we need to have? Temperature. And where do you get temperature from? Take a whole class that half of you probably are in and half of you have already taken it.
Dynamics.
You're missing the first part of it.
Thermodynamics.
Thermodynamics. What do we use in thermodynamics? Well, you use that in this main equation that's like this long.
Oh, the Bernoulli.
No, well, what is the Bernoulli's in that? First law of thermo. There we go. So we use the energy equation, which is the first law of thermodynamics, to find temperature. Okay? So if you ever want to do anything, if you ever want to know the relationship between pressure, velocity, forces, use these two. If you now want to figure out what's happening to temperature, you use the energy equation. Okay? And that's what we're going to do right now. And this is where we left off. So energy. Isn't it crazy how so much you've learned we can now put together?
And you forget so much.
And you forget so much. Yep. That's why studying for your FE is really good, because then it brings back everything and then it helps you actually in advanced classes too. So use conservation of mass and momentum to find relationships between pressures, forces, speeds. And the energy, actually, you could use altitudes, velocities, right? And temperature. So what can we cancel in this? What can we assume about the control volume for Q?
It's the same.
Just assume adiabatic. Yep.
Yeah,
So it's gone.
zero.
Yep. There's no change in elevations. And is there any mechanical work,
None.
any object?
None.
And how many ins do we have?
One.
And how many outs?
One.
Yep. And actually, if you think about it, you see the control volume? You see these sections up here?
Yes.
We neglect those. It's very, 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 very thin, and we neglect it. Okay? So there could be stuff coming out, but we said, screw that. We're not even worrying about that. We're only worried about one direction.
Is there ever a
Okay?
case where there is change in elevation?
When we're dealing with shocks, no, because we're only looking at 1 point from here to here. Yep, okay. We're assuming that the pressures and the velocities are the same throughout, okay? Yep, so I wouldn't even worry about that. Yep. The only time you would really worry about that is when you have most of the time mechanical object like a pump, and you need to shoot water up. That's when you most of the time will have to have elevation. Yep. But for our analysis and looking at fluid mechanics, they usually neglect it a lot of the times. And then neglect gravity a lot. So we have H1 plus V1 squared over 2 equals H2 plus V squared, or V2 squared over 2. And let's just rewrite this. So U2 squared minus U1 squared over 2. Okay, so I just brought to the other side, and what can we call H1 minus H2? Yep, and what can you call delta H? CP delta T. Yep. See how you can get... So what does the energy equation relate? Temperatures and velocities.
No, it's
So the three equations I boxed, so this one with the energy, the momentum, and the conservation of mass, those three, you can do even more algebra to get these equations that are in front of you right now.
No,
Okay.
let's not get the right ones.
And it relates with Mach number. You remember what the Mach number equation was?
Yeah,
I don't know if I gave that to you actually.
I think you might have talked about it. I don't think you gave it to us, but you definitely talked about it for sure.
Yep. Yep. And what was C? I vaguely remember doing this.
C is the speed of light.
No, this is speed of sound.
Oh, okay.
Square root of K R T. Yep. Okay.
3 times 10 to the 8th is the speed of sound,
Times 10 to the 8.
I'm sorry, 10 to the
Speed of light, I think, yeah. Normal conditions, the speed of sound is around 343 meters per second in like standard temperatures. Yep. But you gotta be careful. I mean, so when an airplane says they're going Mach 0.35, that just tells you how fast, but it doesn't tell you the actual speed, right? Because you got to know the temperature that they're flying at in order to find the exact speed. They're flying 30,000 feet up. You know what that temperature is off your head?
Yeah.
What do you normally fly at?
Like anywhere from 1,000 feet up to like 11,000.
What's the temperature at 11,000? Do you know?
It differs.
Typically, what's the lowest you've had? Do you remember?
Oh, I don't know.
No?
I can't remember.
I don't know. I can't remember how cold it got. I should look at some of my data at 30,000
It's
feet.
pretty freaking cool.
It's cold, yeah. Okay, so yeah, those 3 boxes gives you these. Okay, so what I wanted to do is show you how this works and how you can develop these equations. Okay, but you do everything that we've done in the past 13 weeks. Okay, so what I want you to do, I think problem 2 in your homework, take those equations, make that graph.
Negative 56.5 Celsius.
56 at what feet?
That's about 36,000.
Okay, that's pretty cold.
Yeah.
Oh, you can live up down. What are you talking about?
So this is what I want you to make, which is your second page in your back packet. And these I used as text, like the text commands, and I put them in there. Okay. All right. So now you pretty much have the first two done in your homework assignment. All right. Then the last homework problem, well, second to last.
How many are there? 4?
I think there's 4. One of them is the
5,
lab.
So 5, technically. MATLAB.
I think there was only 4, right? Yeah, 4.
Well, I'm counting 5 because that second part on number 1. I count MATLAB.
Oh,
I
you
count
could
MATLAB as.
you could do all this with graphs,
Okay.
okay, and anything else you need to give me, okay, like the scripts. So like this one and like these two,
So there's more than one MATLAB.
there's 4 MATLABs. Yeah, this one is the lab. Remember the lab I showed you? So unzip that file and then get that, and then the graphs are already done for you. You just have to click the plots if you remember that. Okay. This is what I want you to do. Actually, in this one, I want you to draw 2 straight oblique shock waves, which we haven't talked about, and we'll talk about here in a second. Okay. At these angles. Okay. And then I want you to pick 2 of these lines, which is Mach 10 and 1.5 on this graph, and plot that. And that equation is in your book, and I can write that down for you. Okay. So let's talk about oblique shocks. Okay. Questions so far? Alrighty. How do you do the homework? Come, we'll go right to the lab on Thursday. And I can help you. We can sit in a group. Actually, we want to do the AC lab? And there's, what, 6 computers in there?
Yeah, something like that.
Do we have, does everyone, I have 1 or 2 laptops I can bring in. So how many is it? 3,
I can use mine.
6. All right, oh, that'd be perfect then. Anybody else have MATLAB on their laptop?
Probably buy it at some point.
So bring yours in.
Just go see Ben.
Oh yeah, that's right.
Got that working. So
Give me your login username. I will add you to the server list. So however you log into the campus, yep, just give me that and I can add you. That's
Remember how we
right.
used to have to go to the library to log into the remote server to use the Autodesk?
Yeah, they have that for
It's the same server,
Yeah.
but they're not using it for Autodesk anymore. It just sits there. So they're letting us use it for MATLAB.
Cool.
Yep.
From our
So
laptops.
so if anybody else wants that, email me your
Yeah.
username. Garrett, you did that, right?
I did, yeah.
Did you get it working yet or haven't tried?
I haven't even tried.
Okay. All right, Dan got it working. So if you have questions,
I might have to do that.
yep. So Thursday, come right to the AC lab. I'll come down here if you forget. I'll probably try to shoot an email reminding you, and I'll help you. We'll do it right together. I don't care. That's fine with me. Because you're going to need it if you're going to be an FEM and vibrations. You're going to need to know how to do MATLAB.
Again.
Yep. Again. Okay.
More MATLAB classes in the college.
Is more how to, or
Like, yeah.
I try to get you to do
For
them.
how often we use it in our classes, they really should have a little more in depth. It should be like a first year program.
Then have advanced
and then have
MATLAB.
Advanced MATLAB is actually required.
And most of it is like a lot of industries, yeah, they use Excel. But knowing how to program and code is a completely different process in your brain that will help you develop critical thinking. That's why I have you guys do some of these for loops and while loops and all that, just to get you to kind of think differently and will help in the future. So, okay, so let's look at Mach wave. Let's look at oblique shocks, all right? So we have flow going through here. Oh. Come on, I'm trying to delete you. Okay. Wow, I cannot delete that. There we go. So this is a pointed shape So the black are walls, okay, and it could be maybe something like this. And flow is going to go, it's actually going to be supersonic. It's going to shoot that way, okay? What you'll get are these shock waves, which are oblique. They're not perpendicular to the surface, okay? And the angle that it makes is beta from the horizontal. So delta is the half angle of the cone.
So between beta and the whatchamacallit, the blue.
Yeah, I
is
can.
M2.
Yes, so between the blue shock and the walls now are subsonic speeds, which is M2. And this brown line here, the second one, M2, is actually parallel to this black line. Okay? So what I'm going to do now is zoom in on that shock. Okay, does everyone have questions? Understand? This is what happens. The faster you go, these angles will get higher, and that's what I wanted to show you in that lab. Was okay. What is the relationship between Mach number and these angles that are created? So here's this shock, and here is V1, and here is V2. And what I color it was brown. So here is and might as well add, this is your angle beta, just like we had. So I'm going to zoom in. We have V1, we have V2, and theta actually is equal to delta. Like I said, it's parallel to that. Typically, we assume that there's no boundary layer, but in reality, if you want to really do correct analysis, there is a boundary layer, right? Because there's boundary layers in everything. We talked about that underneath a kayak and airplanes. But we typically say, okay, don't worry about the boundary layer. Let's just analyze this, okay? So the angle would be slightly different if there would be a boundary layer, and that's what they call theta. So what do we need to do to figure out and analyze this? Well, let's see if I can do this. We just break these components up. V1T, V1N. So the red that I made on the left are tangent and normal components. And then over here, you can split these two up. V2N, V2T. Nice. And what is the, now what does that look like if you look at the normal ones? It's like a normal shock wave, right?
Kind of.
And that's actually what you use. You just use the normal components of velocities in your equations, okay? So momentum, we had what? P1 minus P2 equals rho 2 U2n squared minus rho 1 U1n squared. And then the energy, we had H1, actually what do we have? CP T1 minus T2, like this? Oh, sorry, you can write them underneath. What did that equal? U2n minus U1n squared over 2.
So that's obviously depending on how normal the shock wave is, though. Right? So about the tangent control.
I don't even need to worry about those, which is cool. Because you only have to worry now about the normal, because those are the only ones that will shoot across the normal shock wave. Yep. Yep. And I think I have something in my head about that I want to continue on and make sure I say it right. Yeah, okay, that's what I thought. So the tangent components, they never change because they're always parallel to the shock. They don't jump across the shock. Okay? So V1T will actually equal, and you can put that in here, V2T. Okay? Because those values, if you think about it, these normal ones are really the main ones that are jumping across the shock. Yeah.
At like the theoretical extreme low, when you look at the whole diagram, you said the shock waves continue to become more oblique and more oblique as it gets faster. So obviously that would, put it at its extreme.
Oh, at a normal shock.
Perpendicular.
Yes.
Right, or
Yep.
I mean parallel.
Yep.
So that would be, it's not existing now. I don't, you know what I mean?
Oh.
It just seems.
You mean this shock wave will keep going like this. So at low speeds,
Okay.
you'll get like a normal shock. The higher speeds, it'll keep going. It'll kind of almost be parallel to that. Yep. Yep. Okay, so we have these, and so really, those equations that you have here, all you have to do is replace the M1 with M1N, okay, which is M1 sine beta, and M2 is M2N, which is M2 sine beta minus theta. So you just have to use the n components in these equations for oblique, and you can figure out what those velocities are. Oh, it's 10:30 already? Holy smokes. That's pretty much all I have. Okay. So just to recap, we talked about isentropic flow, we talked about converging nozzles, converging diverging nozzles, we talked about normal shocks and oblique shocks. Okay. With the homework that you're going to do, basically summarizes all these equations that I showed you and shows you how to actually figure out what the pressures, velocities, temperatures would be before and after the shock. Okay. So come Thursday to the AC lab. Bring, if you have a laptop, bring your laptop. If not, I think there is 6 computers. I'll bring a couple more, and I'll help you. We'll do some MATLAB together. Okay. Okay. All right.
What do you think about